Our next teacher is an experienced distributed systems researcher with a PhD in computer science from the University of Manchester, and has audited the smart contracts of more than 25 blockchain projects. He is the CEO of Cryptonics Consulting, and it's my great pleasure to introduce Mr. Dr. Stefan Beyer.
Okay, so thank you for this introduction. This talk, like the one before, is on smart contract security. I want to look at it from a different angle than the previous talk. What I will do is I will talk about the number of known vulnerabilities, and I will provide solutions and discuss them. And I will order them I will prioritize them according to how I find them in the audits I've done, and prioritize very common vulnerabilities first. So, but before getting into smart contracts in particular, let's just talk about blockchain security in general. Are blockchains secure? And that's a question I'm often asked. And I mean, what do you think? Are blockchains secure? Yes, if you nodding heads there. Yeah, I mean, cryptographically speaking, as long as you're using a well-established blockchain, something like Bitcoin or Ethereum, you should be on the safe side. They're fairly secure, the math is sound, and it has not been broken yet. So I say usually yes, but the digital assets that we represent on the blockchain, they are not secure. And that's a bit of a problem, because the blockchain is all about digital assets. I mean, usually we move money around, or we tokenize real estate, art, or whatever, but there's usually some value involved, some form of digital asset. And just to back this up, here's some facts. In 2018, according to one report I read, 1.7 billion in digital assets were stolen or lost. Now, there's obviously not a central place where these things are reported, so depending on which report you read, you get a different number. But I think we can all agree that it's a lot of money that generally gets lost on the blockchain. And even more worrying from my perspective is that one report I read identified two groups which were responsible for the majority of attacks, or for a large number of attacks. And again, it doesn't matter if it's 2 groups, 3 groups, 5 groups. The important takeaway here is that it's become a business model. So there are people that specialize on stealing funds on the blockchain, and it's obviously a profitable business for them. Otherwise, they wouldn't be doing it. So what are the security concerns? Well, I've classified them a little bit, and what we're going to talk about here today is smart contracts. So I won't say anything more right now on this slide, but let's quickly talk about the other worries there are. There's usually a lot of off-chain code involved. So the blockchain, the cryptography might be secure, but the code that is used to access the blockchain might not be. And this includes databases that hold keys. Key management is very difficult. It includes web applications, APIs, that sort of thing. So there's a lot of traditional cybersecurity involved. There's infrastructure. Blockchain nodes need to run on hardware. This hardware is connected to network. The nodes and the network might be configured poorly, so there's security issues there. And finally, there are humans involved. Usually humans interact in some way or another with the smart contracts, and humans are the worst enemy of cybersecurity because they're generally lazy or do things that are not expected, and they're really not very good with things like key management. And we find that in a lot of incidents, the human is actually at fault. But let's talk about smart contracts. So I don't want to give too much of an introduction what a smart contract is. Usually this drink machine is used as an example because it's an automation of interactions of some transaction. In this case, it's a hardware implementation of some terms, how much I have to pay to get a can of Coke, and what happens if I don't have or the machine doesn't have any change. So these are terms coded into the hardware there. And this sort of, Nick Szabo mentioned this in '96, so it's not a new concept, but yeah, smart contracts have been around for a while. But obviously when we take this to a blockchain, something like Ethereum, which is almost Turing complete, a smart contract is just any code that runs on the blockchain. And what I want to say here is the type of smart contract that concerns us is that there's actually some terms involved. In order to make it a contract, we need to automate some sort of value transfer or have some terms coded into our code. I could write a program that stores the name of my wife forever on the blockchain, and that would be a smart contract, but it's not a smart contract that is interesting for this type of scenario from a security point of view. So the problem with smart contracts is, well, they have three properties, which are both good but also problematic. First of all, they're publicly accessible. Anyone can read them on the blockchain. They generally hold some value, at least the smart contracts we are interested in here. So there's something to steal. And they're mutable, which is good because otherwise anyone could just change the terms of the contract. But it's also a problem in that if I deploy a smart contract and there's a bug, it's hard to fix it. The only way to fix it is really to deploy a new version of the smart contract. So this just converts them in a very interesting target for cyber criminals. And here are some more statistics, just looking at my own smart contract audits. These are the statistics for 2018. They've since been changed, but the trend is the same. I audited 22 projects, and there's a number of issues that I found, myself and my team. But the interesting, I mean, this is not evenly distributed. There are very good projects and there are very bad projects. But what they all have in common is that not a single one was flawless. And that's interesting. Now, this tells us two things. First of all, my team is quite good at finding these things. But no, what it really tells us is that getting smart contracts right is something extremely difficult. And even very good teams don't manage to do that flawlessly. So, having given this short introductions on what the issue is with smart contract security, let's just look at a number of vulnerabilities. And I'll start by showing some code. Now, this is the reentrancy vulnerability, which is probably the most well-known Ethereum vulnerability, just because of historic precedents. Right now, most programmers are aware of this, and it shouldn't happen, but it does appear occasionally in audits. Okay, right? So, can you see in this piece of code, I assume you all have some programming experience, so this doesn't have a pointer, never mind. So basically here we have a balance. There are balances kept. Which amount of ether belongs to whom, and there's a payout function, and anyone can call this to request its own ether to be paid out. Now, can you see what's wrong with this, where the danger lies in here? Yeah. Yeah, exactly. So you pay out the ether because you reset the balance to zero. And if you think about it, this happens within a transaction, so it's atomic, we would think, right? So it shouldn't matter. There shouldn't be a race condition. But there is, because this call here, this where the balance is transferred, is actually an external call. And in case the address we send the money to is a smart contract, this smart contract actually can execute code. And what this code can do is call back into the contract and call payout again. And because the balance is not zero yet, it will succeed until the contract is drained, right? So the change of concept here is that you have to assume that an address can either be a person, an externally owned address, or it can be a smart contract. So any external call is dangerous. So how can we prevent this? Well, there's two solutions really. The one that is often used, and which I don't advocate, is to use a gas-limited transfer function. Right? The function I called there to transfer ether. forwards all the gas to the calling contract. But if you use something like transfer send, that's limited, and it actually limits the gas that the caller can spend, so that it cannot do much. It's actually not enough to call back into the contract. The reason I don't recommend this is because smart contracts are very long-lived and the protocol may change. And back in January, when we tried to do the Ethereum Constantinople update, we almost messed this up because for some invocations, the gas limit would have changed, and then re-entrances that were not thought to be possible would have been possible again. So what we should really do is to not change the state after an external call. Be aware that an Ether transfer can be an external call. And there's something called the checks, effects, interaction pattern, where you first do the checks, then you calculate the effects on the state, apply the state, and then you do the actual interaction. The case this was first sort of exposed at a large scale was the DAO hack. You've probably all heard of this. If not, it's a very interesting case, so please read up on it. But basically there was a crowdsourced fund which held 12.7 million Ether at a single contract address, which is almost always dangerous. A lot of money at a single place. And what happened is that there was a reentrancy vulnerability. It led to the creation of a child DAO, which was sort of a mechanism that allowed the team to lock the code for the funds for 28 days. So the community actually had 28 days to try to recover these funds. And the fallout, we've all heard of. It led to a hard fork in the Ethereum blockchain. We had a temporary Ether price crash, although that doesn't last long. And the DAO eventually collapsed. But anyway, a very high profile case, but after that there were others. Right, the next vulnerability I want to talk about has to do with integer arithmetic. And this, I mention this here because I do find it quite a lot in audits. And it's interesting because it's something that we should be clear by now, and it's not unique to blockchains. When the banks automate their financial systems, or they automated their financial software in the 1960s, 70s, they already came across this. But basically, when you do arithmetic with integers, then you can get overflows or underflows. So the very simple example here, if you have an unsigned integer and you subtract 4 from 3, you don't get -1, you get a very large number. It's a bit like the mileage meter in a car. It turns over and it starts again. So here you've got a very large number. And here's a real-world example that I actually found in one of the audits I did personally. This here is it's a game implemented in smart contracts, and there's some fees involved. So the owner takes a cut, and there's also a cut sent to a charity. And this function here, just cut, allows to the owner to adjust the cut, but there's this condition here that it can only take 5%. This less than 51 means the maximum of the combined fees is 5%, right? So if you look at this code, can you spot how this might go wrong? Yes. Exactly. What the owner can do here is he can put a very high owner cut and the normal charity cut, and if that overflows and is below 51, then that succeeds. And depending on how the rest of the contract is implemented, this means that the owner can actually get 100% of the fees if he wanted to. Now in this case, I believe it's intentional, but it's important to think about these things. In this case, the require statement should be for each of these. Another famous incident related to overflows was the ERC20 batch transfer. So this is a code that is around quite a lot. As it often happens in these open source projects, is that they copy code from one to another. And there are ERC20 implementations out there that add a function to the standard which allows to batch transfer funds to to a number of addresses at the same time. So here it takes an array of addresses. So there's a number of addresses that can receive funds, and there's a value. But actually there where it says amount equal counter times value in the second line in the function, there's no check whether this can overflow. So this can actually overflow, and it means that the check passes because the checks are on, the required statements pass. But then when we actually subtract from the balance, that still passes, right? Because it's not the real amount. But the transfer, we do use value, the individual values. And this basically means that someone that uses this can trick the contract into paying out much more than it should. And that was exploited in April 2018 in a project called Beauty Chain, and a lot of other projects had to change the implementation of ERC20 because of this. Now, very related to overflows and underflows is the subject of integer division, integer precision. So whenever you do calculations with integers, particularly divisions, you lose precision because things are truncated. You don't have a remainder, right? So if I have integers and I divide 5 by 2, I don't get 2.5, I get 2, right? Because the 0.5 is chopped off. So the way to avoid this is to use a multiplier. It's good practice to multiply this by 10, and in this case here, we would divide 50 by 20, and we would get 25. And then we would deal with 25 at the application level. We interpret this as 2.5, which is the way financial software has worked for ages. You know, usually have everything in cents instead of dollar, just to avoid this. So best practice here is obviously to check for overflow and underflow. There are safe math libraries out there that you can use, and they're highly recommended. The Open Zeppelin one is particularly good. It's a well-known smart contract library. You have to use multipliers to avoid precision and to avoid truncations. And whenever you do arithmetic, you should worry about the order you do things in. And this is very common when you calculate percentages, because what you normally do, you multiply by 100 and you divide by something. And you know, by the rules of mathematics we learn in school, it shouldn't matter which order we do things in. But in integer arithmetic, if you divide before you multiply, you actually have less precision. So if you multiply before you divide, that's actually better. Okay, moving on. This is something that is less easy to spot, but happens quite a lot in the contracts we audit. We call it the revert denial of service attack. I'm not sure that's the official name for it, but that's what we call the vulnerability. And the scenario is very simple. Basically, you have a transaction and you do some stuff. Then you make an Ether transfer or a similar external call, but you make a transfer. And then you do something else. And an Ether transfer can be an external call, as I said before. If the caller is a smart contract, then there's some code being executed. And this code can do a number of things, including it can always fail, right? So the attacker can make this just fail every time. And this means that the rest of our transaction is never executed, because transactions are atomic, they fail altogether, right? So the whole code is never executed. Now this is an example here. It's a very simple auction, sort of a naive implementation of an auction. And the way it works is people make their bids by sending Ether to this bid function. And if the bid is higher than the previous highest bid, the sender of this transaction becomes the current leader, and the earlier bid is refunded, right? So any idea how this could be exploited? Can you see what could go wrong? Yeah, as I said, these are a bit harder to spot, but what could happen here is I could call this from a smart contract, and I could I could send my bid, which is higher than the previous one. But whenever I get a refund, when something is sent to me, I just don't accept the money. I don't accept the refund. So I make my fallback function, which accepts the ether in my smart contract, I make that revert. So I basically reject the refund, which means the whole transaction reverts, the whole transaction fails, and no one else can ever exceed my bid, right? So I will always be the winner of this auction. So this is a bit harder to spot, and it happens quite often in smart contracts. So important for this is we have to assume that any address may be a smart contract, and then it's an external call. Smart contracts can implement a fallback function which executes any code, and that might include just failing, and that will make my whole transaction fail. And what we should do is to any isolate call or any ether transfer to isolate it as much as possible. And there's something called the pull and the push pattern. Well, there's pull over push payment pattern, which means you should not push out funds to anyone. It's best practice to make them claim any payouts. So the way you do that, you have a withdrawal function. In the case of this auction here, you would just mark the previous bid as refundable and then finish the transaction. You don't make the refund in the actual transaction. And then the previous leader can request the payout, and this payout is isolated in a single transaction, and it cannot interfere with anything else. So that will make this piece of code safe. Slightly related in that it's sort of a denial of service scenario, a homemade denial of service scenario, is problems with the block gas limit. And this I see a lot in smart contracts, in the audits. Basically, Ethereum doesn't have a fixed size limit for blocks, but it has a gas limit. So all transactions cost gas, and when they get included in blocks, this is added up, and when it exceeds, I think it's currently 8 million gas, then the block has to be closed. It cannot be bigger than that. And this means if a transaction grows too big, it just won't fit into a block anymore, right? So how can a transaction get too big? Well, here's one example. This is a payout array, which can grow dynamically. It's of variable size. And then there's a payout function where we actually push this out to these addresses. So this iterates over a variable size array. And that's a problem here, because if this array grows too big, then it will, this transaction here would cost too much gas, and it will not fit into a block anymore. So if there's no other way to get this ETH out of the contract, it will be stuck forever. And this is a typical example of people not thinking about how that, at scale, how their transactions or their contract deal when the product becomes really popular. And yeah, iterating over arrays, if they're of variable size and can grow dynamically, that should be avoided at all cost. So yeah, as best practice here, obviously we have to be aware of the gas requirements of our code. We should avoid this iterating, as I just said. And if it is necessary, because sometimes it might not be avoidable, do it in blocks of 100, for example. Right? So in this case of making payouts, make 100 process 100 payouts at a time. And again, the problem here was we are pushing a payment out. It's easier to just make these refundable, and then they can withdraw them. So the previous talk talked a lot about front running. So but I see some different faces here. So I'll explain a little bit about it. But basically, for transactions to be included in blocks, they are sent to the blockchain, and then they're in something called the mempool, visible for everyone. And miners pick them one by one according to some algorithm, usually based on their profit, maximizing their profit. So these transactions might be for a while in the mempool, and anyone can read them. And the issue here is that if I can read transactions and they might be of interest to me, I can just try to overtake them. And the way to do this is to incentivize the miner to include my transaction first. And that I can do that by increasing the gas price. And when I first learned about this some time ago, I thought of this as sort of a theoretical issue that doesn't really happen in practice, but it does actually happen quite a lot. And I'm going to show a couple of examples. So the first one is sort of my contrived example of this. It's a simple lottery. Basically, it's guessing a number, and you submit a hash of this number. Well, actually, I think there's something missing. But anyway, there's a play function where you send a guess. And this guess has to be, the hash of this guess has to be larger than a difficulty parameter, which is the way Bitcoin mining works, right? That the difficulty and the hash sort of has to match this criteria. But anyway, the point here is this is visible on the blockchain, and if I find a valid solution for this lottery, this transaction is on the blockchain in the mempool. Someone might see it, pay a higher gas price, and just resend the same number, the same hash. Sorry, the same number, and the same hash would be calculated. A less contrived real-world example is a bug or a missing feature in the ERC20 specification. So the ERC20 specification, as it is officially accepted, actually has a vulnerability in the approve method. Now, approve allows me to approve someone else to spend my money. So I can approve someone to send 100 ETH on my behalf. And the problem there is if I do that and set it to 100, for example, and then I change my mind and want to set it to 50, if someone who watches the mempool times this right, can actually, with front running, spend 150, which is 50 more than I originally wanted, and certainly more than I wanted to spend after changing my mind. So the way people usually avoid this now is to always make an approve 0 before changing the number. So if it's 100 and you want to change to 50, you have to change it before that to 0 and then to 50 after the transaction has been accepted. Another way is to have an increase or decrease approval method, which is not part of the standard, but it's implemented quite often. And also the early version of the bank or smart contracts, sort of a decentralized exchange scenario, also had a front-running vulnerability. So best practice, well, we have to be aware that transactions are visible on the blockchain. We have to think about the order in which they can be executed. And there's a contrived way to solve this by placing an upper bound on the gas price in smart contract logic, but that just means no one can pay a higher gas price. But that's very difficult to do, and it's sort of a dirty workaround. I don't like that one. The best way to deal with this is to have a commit reveal scheme, which Cheyenne, the previous speaker, explained quite well. So if you can look for more detail at his slides, but basically it means you have two transactions. The first one you commit to a value by sending a hash, and in the second one you reveal this number, and that way you can't be overtaken. So the next vulnerability here is an interesting one, and I'd never expected to see that often, but I've seen it 3 times in 3 different audits already this year, and that's a signature replay vulnerability. So what a lot of people do, instead of letting the Ethereum node verify signatures, they compute signatures off-chain and transmit them in bulk, which is often done for efficiency, but it can also be done in sort of a multi-signature scheme where you have to submit 5 signatures to approve a transaction. And very often people that use this don't know the basic cryptography, right? So I see that a lot, that there's basic mistakes that lead to signature replay vulnerabilities. And signature readable vulnerability is very simple, even away from the blockchain. So you have Bob send a signed message to Alice. And of course, Eve can just listen to this message and copy it and just resend the same message. And the signature is still valid. Because what signatures actually do, they just identify the signer and they ensure message integrity. So the message cannot be altered, but it can be resubmitted. So there's nothing more in this actual signature process that prevents Alice from receiving this several times and thinking it's from Bob. Now, of course, it's a message signed by Bob, but Eve can just send it again. So if Bob and Alice want to keep track of which message has already been received, they have to implement this. They have to put something in the message that identifies the message number or something like this. And that's not part of the cryptographic primitive. That's not part of the signature. That's something that goes on top, and people forget about this. So this is a code example from a very big project that I audited recently. This was actually a bridge from to move Ethereum onto another blockchain and back. And this is real code, but I've shortened it a bit to make it fit on a single slide, but it's from a real project. And basically, there's this unlock function on the Ethereum side that unlocks Ether locked into a contract. And it needs a number of signatures to be submitted to the smart contract to work. Now, it validates the signature using this built-in EC recover function, but the message it validates it just includes the sender, the receiver, and the amount, right? There's nothing else in there. No message number, no nonce, nothing. So the way to exploit this would be Bob has 10 ETH locked into this contract. Alice collects the necessary signatures and calls the unlock function and sends 10 ETH to Bob. So it's all fine until here. But obviously this transaction is on the blockchain. Anyone can read it and can just copy this message, this transaction data that was sent, and copy the signature array and submit an identical unlock call. So Bob can do this again, or Eve can do it on his behalf. But the point is, Bob can receive 10 ETH as long as there's money left in the contract. So he can drain the whole contract. So how can this be avoided? Well, the first big point is don't try to do things with cryptography unless you know what you're doing. A lot of smart contract programmers are from a different background. They don't know the internals of cryptography. So before doing something like this, make sure you understand cryptography. And then, you know, what should be done in this case? To use a nonce, which is a number used only once. So basically you put each of these calls is numbered. Each message has a unique number, and you keep track of which ones have been used before, so they cannot be replayed. And another good practice is to include the smart contract address also in the signed message. And this is important to avoid replaying transaction from one blockchain to another. Because if the smart contract address is unique, then this type of replay attack can also be avoided. This can, for example, happen if a project has been deployed on the testnet for a few months and then moves over to mainnet. Someone could just look at the testnet transactions and copy the signature arrays and get done with it. So that was just a small selection of vulnerabilities based on those that I see a lot in the wild. There are much more out there, and as you've seen on this slide with statistics, there are hardly any flawless projects. So it's important to think about getting a smart contract audit, even if even for very good teams. These projects that I've audited, they were not idiots. They were very good programmers, but you need external eyes on things. And smart contract audits are not cheap. But compared to the marketing budget of most of these projects out there, it's actually minor. And having a good audit report is actually very good marketing. apart from the fact that it saves you money afterwards. Yeah, that basically sums up everything I wanted to talk about. Open for the Q&A. Yes. So the question is, in the last example, if there's a nonce, I still need to use the smart contract address in the message. Is that correct? Well, yeah, I mean, if you have a nonce, this code is safe, it's secure, right? If you put a nonce in there, then you obviously have to check for the nonce within this this unlock function, and you have to make sure it's not been used before. But what happens if the same contract was deployed on another blockchain, right? On the testnet, for example. Then theoretically, if the nonce has not been used, that nonce on there has not been used before, you could still replay a message from there. It's less likely, but it's considered good practice. Thank you.